of researchers with similar interest in energy system. Actually, it's really exciting time to gather and talk about the energy system as our workshop coincides with COP26 happening in Glasgow now. So it's a really timely workshop. I'm Zoya Pourmirza, Research Associate at Newcastle University, and I'm working on energy system digitalization with the focus on data, cybersecurity. And Dr. Sarah Walker will chair this workshop. Sarah is the Director of Center for Energy and National Center for Energy System Integration, CESI. And also she's Deputy Director of Supergen Energy Network Hub and Active Building Center. So now let's have an overview of what energy system digitalization is and the topics of our presentation today. Okay, in 2019, the UK government committed to achieving net zero carbon emission by 2015. This was compared to the previous target of an 80% reduction in emission by 2050. The government considered digitalization as a core component of UK net zero target and not just as an enabler. They also estimated that digitalization could reduce the overall cost of UK energy system by up to £10 billion annually. So now what does digitalization do in energy system? It can support decarbonization and decentralization of energy system. It enables widespread use of renewable resources. It can improve flexibility, and it can create innovative products and services. So what energy system digitalization is, it refers to the integration of various forms of energy system with technologies such as IoT, AI, digital twin, distributed ledger technology. This technology can make energy system to become more connected, more sustainable, and more reliable. And they can also support data analysis. They can provide peer-to-peer energy trading. They can provide more services. They can also allow deeper penetration of renewable resources. So a part of the benefit of digitalization in energy sector, there are some challenges as well, such as data challenge, including data availability, lack of data governance, interoperability, and lack of data standards, and cybersecurity, which is the topic for the workshop tomorrow. Today, we are going to have 5 fantastic speakers from Australia, Denmark, and UK. The first talk will start with talking about digital energy initiative in Australia. The second talk will walk us through the digitalization journey in Danish energy sector. We will also have presentation about data governance challenges in the UK, about how to deliver a modern digitalized energy system, and predicting the impact of climate change on performance of energy system using machine learning. So the timeline of this talk would be like, we will have 5-minute introduction to the Center for Energy by Dr. Sarah Walker. Then we will have 1 hour of presentation. We will have 4 presentations, each 15 minutes. We will have 15-minute breaks. 15 minutes break, and then we will have another presentation. And after that, we are going to breakout rooms. So, when presentations are all delivered, we are going to assign you to a number of different breakout rooms. For 45 minutes in each room, we will need someone to volunteer and take notes, recording and saving the whiteboard discussion. Please use the whiteboard to write down your notes. And we would encourage you to take this time to introduce yourself to each other, and then discuss the 3 questions that you can see in the next slide. So, and then each question will be about 15 minutes. And once everyone is back in the main room, the room lead will present a summary of the room discussion. And this is a good opportunity for you to hear from other groups and ask any question if you have any, actually. So now let's see, in the next slide, we will have the 3 questions that we will discuss. And yes, that's it. So now without further ado, I will give the floor to Dr. Sarah Walker to introduce the Center for Energy. So over to you, Sarah.
Thanks, Zoya. So here at Newcastle University, we have a Centre for Energy, which is focused around bringing together the community of researchers who touch on energy in the research and teaching work that they do. And our vision here is to unify those efforts of staff, regardless of job family. So this means academics, researchers, technicians, professional support staff, to unify those efforts and to raise our ambitions around new ways of thinking about energy systems. And by new ways, we mean that we're thinking about working across scales. So this could be from electrons all the way through to global trading systems. We mean across geographies. So this could be an individual household all the way through to megacities. Across disciplines, so engineering, social sciences, law, public health. A multitude of disciplines are needed to address such a complex problem. And across applications, so applications in industry, applications in the domestic use, applications in transport, for example. And we've structured the centre around 3 key themes to work on energy. And these 3 themes are around justice and ethics, which covers issues like energy behaviours, business models, policy and regulation. Around energy itself, but this goes from materials through to technologies, through to design of systems and demonstration. And then our 3rd theme is around security and resilience. And this includes sustainability, systems infrastructure, and digital innovation. So in this space, working on energy, we quite often talk about 4 drivers of change for the energy systems, the 4 Ds, and that is around decarbonisation, around decentralisation, around democratisation, and around digitalisation. So as the centre, we're really supportive of this initiative of the 2 workshops and really looking forward to having some discussions around that driver of change, digitalisation for the energy sector. Thanks. So a very brief summary there of the centre, but I will kick us off then with our first presentation and invite Professor Ariel Liebman from Monash University to give us our first talk on digital energy initiatives for the energy sector in Australia.
Thank you. Can you hear me okay?
Yes.
Audio working well. We'll put the right microphone going.
Yes.
And I'll share my screen now. Can folks see that?
Yes, that's come up. Thank you.
Excellent. So thank you very much. I'm honoured to have been asked by Sarah and Zoya and the team at Newcastle University. So I'll talk about this transition or the digitalization for the energy transition from a sort of Monash activity perspective. It's one of the ones that I'm most qualified to provide, but it's probably worth saying that the way we structure our work, we have a very similar philosophy to your centre at Newcastle, is that it's cross-disciplinary and we focus on really material challenges that face the whole sector. So we're very much inspired by the needs and the activities of the Australian energy sector. So everything we do has a context in solving a real problem we're facing in Australia. And given that Australia is perhaps at the bleeding edge of aspects of the energy transition from electricity, not necessarily in a good way, but in a way that exposes a lot of challenges. So hopefully this is useful for folks around the world. So this is me. I'm a Professor of Practice in the Department of Data Science and AI in the Faculty of IT at Monash University, and like Sarah, I'm Director of our equivalent institute, the Monash Energy Institute. Why are we doing this? Well, I think I probably don't need to preach to the choir here. We need some significant action, and as is happening just up the road from in Glasgow, people are talking seriously about how we're going to find this a way to get down this 1.5 degree trajectory, which is, to me, is the only one worth aiming for. Even it itself is not necessarily likely to reduce the risk of climate change. So we have a strong history in the last 10 years or so of working at Monash towards some of these objectives, particularly with our net zero emissions by 2030, for which we won a UN Momentum for Change Lighthouse Award at COP24. That was something that I had the privilege to be involved in the development of, and a range of other things, which we, I guess, are quite committed to. So that's sort of our bona fides as to the fact that we are keen to make sure these things happen in earnest. A little bit about our Monash Energy Institute. It's a internal joint venture between 3 faculties and our Net Zero Initiative, Faculty of IT, Engineering, and the Monash Business School. And we focus on sort of 3 impact areas: advancing new energy solutions, accelerating the energy transition, and making sure that all of these first 2 are done in the context of really what people, human beings, we call them consumers these days, which is a little bit of already a little bit of a funny term, because they're much more than consumers. And we have several themes which sort of represent our sort of vertical capabilities across the university: materials and devices, energy resources and clean hydrogen, clean fuels and hydrogen, smart energy systems, markets and policy, and consumers. Excuse me. So there's just an example of the people we have. We also have a very diverse team, not just academics, but also people who run our facilities to make sure we have embed a culture of collaboration between our facilities people who run what we call as our Living Lab Microgrid, as well as our net zero transition, and the researchers in the university. We work closely with industry and others. So a few major initiatives that are probably not worth going through in detail right now, but you presumably can have a look at these slides later on. So what are the 2 things that I wanted to talk about? One of them is our microgrid. Now, microgrid is a bit of a funny term these days. Who knows what it really means? So we define it, you know, as we wish these days, I find, all around the world. So our microgrid is really we get as close to being able to disconnect our campus grid from the rest of the system as possible, without trying to generate without being able to generate the majority of energy on our campus. The only way anybody can do that is through a lot of consumption of a lot of gas. In the future, we might be able to do it through renewable hydrogen sourced elsewhere. But in the meantime, what we try and do is make sure that it has all the elements of a microgrid in terms of its smart characteristics. So this is part of our commitment to get to net zero, serving student growth. Now, some of these projections are a little bit old now, given COVID. And COVID's really affected our growth projections in Australia quite significantly. And nevertheless, the need to save energy is still, and reduce emissions is still significant. We are already effectively sourcing 100% of our renewable electricity from a wind farm that we helped underwrite in combination with rooftop solar and energy efficiency retrofit. So we're reducing our per capita electricity use on campus and meeting as much of that electricity as possible from renewable sources. Some of a component of that is not the full wind farm, but we can certainly say that it's generating an equal amount of renewable electricity based on our contract. Of course, there's certain swings and roundabouts with our clean energy certificates, which we will then transition to being fully on paper renewable over the next 2 or 3 years, well before 2030. So our campus, we set it up so that one of our 3 sub networks, which is where these purple buildings are on and these red, yellow and orange buildings are. And this is where we're building our active energy precinct, which is effectively our microgrid. It's got 25 buildings with diverse loads, commercial, office, teaching, residential, and a new net zero smart building, which is the Woodside building, where our institute is housed. We've got 3.5 megawatts of peak demand on that network and 2 megawatts of solar. So it's fairly well balanced in peak production times. And in fact, it could be that there were times where there'll be more solar production than consumption, depending on the time of the year, whether many people are on campus or not. We have EV charging and also a 1 megawatt hour battery. So we're learning now how to orchestrate these to sculpt the load of that part of the campus. So as we said, it's got, and the most difficult problem is the flexible buildings part, which I think Sarah and the team know well. Trying to make building management system managed buildings, traditional buildings, change their energy use on command is not that easy. And so this is where some of their digital energy research comes in. So what do we want our microgrid to do? We want to digitalize it. I'm not sure if, digitalize sounds funny, digitalization sounds better. But we certainly can't digitize it. There will be like in Tron, zapping it and putting it in the computer. We don't know how to do that yet. So we want to make it a flexible participant in the broader energy system with a range of possible future participants who are going to be seeking to pay us, hopefully, for our flexibility. And we've done it in hardware. We're still in the process of actually getting the software running on this hardware platform. And the hardware platform we've developed is in partnership with an organization called Indra, a Spanish company, which provides a range of hardware, middleware, and software for complex infrastructure systems, including grids. And so we've enabled our microgrid component, part of the grid of our network that is a smart microgrid with a range of these technologies. And it looks like I'm going way over time. Is that right? Oh no, that's right. I started the presentation officially a bit earlier. How much time have I got? Can someone tell me?
Yeah, you've got about 6 minutes.
Oh, good. Right. I think I can do that. So this is the hardware. Writing the software for it is probably harder than getting the hardware to work. So the hardware is working, but now getting the right software, which doesn't yet exist, to help coordinate all these resources is the trick. So some of the software exists, some of the software doesn't exist. And that's another example of digitalization software. This is our visualization team showing different ways of viewing this. And there's a much more active version of this where these different buildings, energy use is visualized in this way. So we are structuring our operation, looking at all our people, all the sources of load on our campus as customers. And the reason for this is that really once you've take this view, you realize that if you can make this work on a university campus of this scale, or at least this part of the university campus even, then you really have a microcosm of many real world precincts. And so when we finish this, we will, as we go, even before we finish, we'll have some learnings to share with partners, and we still want to learn from partners. So this is one of the things that we will be pursuing with Sarah and the team over the next couple of years. The vision is turning groups of buildings into virtual power plants. Effectively, that's what we're trying to do. And so there's several challenges inherent in this problem. You can't really do that anywhere near as easily as turning a large battery into a virtual power plant, or even a collection of small batteries into power plants. Number one is, well, first of all, you have to wire everything up. And so this is an example of what we're doing, wiring up all our different solutions, all our different resources into a single platform of communications and computing, edge computing. And that's certainly not off the shelf. And then once we have this, which we're still in the process of, we need to be able to merge all these different sources of data, HVAC data, set points, and various things, and then control those set points in response to a model that we build of the building, forecasting and control of the building. So some of the work we're doing is now trying to learn the response of a building to different changes in set points. And currently the best way to do it is to do it through a generic building model. Because trying to get a building model, a computerized building model in something like Energy Plus, which we're using the generic model, because the real model, who knows what that is, trying to simulate your building in real time requires a lot of data and no one has generally. So we're testing the algorithms on representative data, and then the next step would be to then use the learning, and we're using a combination of reinforcement learning and optimization and machine learning to develop these and then deploying in the real world. We've done some experiments, but they're still being analyzed, but we will have to do a lot more real life experiments. And so that means that eventually, and this is what the hope is, that for flexing any of these commercial loads around the world, we go from a passive energy management system through to an active and then a transactive energy management system, where the decisions are mediated by various price-like value streams. So now I'll skip through these. These are some of the other technologies we're deploying, including making sure that the whole grid that we have doesn't just flex and does what it wants. It has regard into the power quality work. And so we can go to our website and find some of the publications around that there, or rather this is the Microgrid website. And I can share, I think I've got some links later on. So what is it that we're actually doing when we're doing the research that applies to that? And this is work that is applied to a range of things in Australia. Forecasting is something that's very important, both microgrid level or community level networks, as well as large-scale wind and solar farms. So on a small scale, there's work being done at Monash around hierarchical forecasting of electricity demand. So that's an area that's emerged out of the standard time series forecasting, and but with better data, but sparse data, more granular data, like individual houses as well as aggregated. There is various methodologies that are developed, and it's not in my area of expertise, but I believe these yield some pretty good results for individual as well as aggregate loads. Another area of work we have, which is of course quite familiar to a lot of people, is this non-intrusive load monitoring. And this is work that my colleague from electrical engineering, Reza Razagi, has done using machine learning and looking at data as if it was an image, and using some algorithm inspired by image processing to try and detect flexible loads, such as flexible pool pumps in a residential building. So similar methodologies would apply to detecting things at a larger scale. But things are still getting still a little bit hard to detect anything real at the non-residential scale because of the complexity of the loads of large buildings. Another area that will be talked about a bit more is cybersecurity tomorrow. So our approach to cybersecurity is using a virtual power plant type model of distributed energy resource orchestration, then trying to understand how false data injection attacks can benefit attackers, and then how do we detect and remedy them. So that's work being done by Tusita, and that's marrying up optimization, machine learning, anomaly detection specifically, and then cybersecurity. So what's clear, of course, from all these use cases is that no one or other aspect of computer science or AI will actually solve the problem by itself. So another area, this is in fact what
Ariel, can I just say that we're just running out of time now? If you could finish up, sorry.
Yeah, that's right. My bad. So this is another area where it's related to the previous one. And the last thing that I wanted to touch on, or two last things. One is the work on coordinating smart inverters to manage load curtailment. This is an application of optimization. And then one case study is about coordinated generation transmission expansion planning. And this is an area that's needed to build the modern grids, where we really have to plan the grid generation and storage at the same time over 20-year plus horizons. So yeah, that's really all I wanted to cover today. Some more information there about the technical aspects of this. And then the last slide here, you can find the various links for the facilities. So thank you very much, and apologies for getting over time.
Thank you very much, Ariel. So I'll hand on to our next speaker now. So that's Dr. Razgar Ebrahimi, talking about the digitalization journey of the energy sector, the Danish use case. Razgar, over to you.
Yeah, thank you. I'm just sharing my screen. Yeah, I guess you can see my screen now, right?
Yes, we can. Thank you.
Perfect. So thank you very much for the invite, Sarah and Zoya. It's great to be here. And when it was suggested by Zoya initially, we thought it was really interesting, and also to find people who work in the same area. So I'm going to talk about what we do here, at least at DTU, in terms of digitalization in the energy sector and the work we do around this area. So I'm a researcher at the Department of Applied Mathematics and Computer Science. Our work is mainly around optimizations, time series analysis, and with mostly the domain of the energy sector. So we do quite a lot of work in this area. Okay, so I'll tell you about a bit about the digitalization, how we see it, why it is important, and a bit about Center Denmark. So, and then a project that we have in the same line, and then what Center Denmark is about, the digital platform ecosystem that we are trying to build, and some R&D use cases that we have. So we have recently been commissioned by Digital Energy Agency, DA, in Denmark to do some work in this area, and also to find out, mostly with the focus on DSOs, what the digitalization is and where we are at the time. So in fact, what we have seen is that so when it comes to digitalization, I think it's a kind of mix between digitization and digitalization. So so digitization basically means we are going from the analog to digital, and then when it comes to digitalization, it's more about upgrading or putting new hardware setups. But with what we have witnessed, at least here in Denmark, is that at least in the industry level, we are somehow in between the two, but for the science and development, we are more towards digital transformation. So we are a bit ahead, but we are forgetting that maybe the industry is not ready. And most of the work that has been done is around digital transformation, where the focus is on the data. So the assumption is that all the DSOs, all the partners have the necessary setup in terms of the hardware, smart meters, sensors, and all the in fact the systems, and then we are able to get the value out of it. So this is sort of the big picture we see, and actually it's quite interesting. Lately there was also a report out from the UK that I believe both Sarah and Zoya have contributed. We have seen a lot of sort of like work that were more or less similar and complementing each other. But just to say that at least here in Denmark, where we started more focusing on the data side and data transformation, we came up with or at least at the board, the needs for digital data or digital data providers, platform providers. So why is the digitalization important? Of course, we all know they are complex systems, and they are not only complex systems, but they are highly interdependent. And since we are in a transition to become really more smart energy systems, I mean, the word smart is quite important, because depending on the disciplines, we have different perspective. For some, it's just having the smart meters in place. For some, it's about the whole system where you can make this intelligent decision. So we are, at least from our side, we think that we are still in a transmission, in a transition period. We are not there fully, but we are on the right path. And of course, it's quite important in this digitalization that we rely on both real-time and historical data for operations. And not only that, because when we say systems are interdependent, it requires interoperable solutions. So we cannot just, it's almost impossible to have a solution in this area. We need to have many solutions that can work together. So coming back to the data, it was, at least in Denmark, what we saw, it was the need for providing a national center. And this is why the Center Denmark was established, with the same idea that we would have a place for where everyone, at least within the energy sector, both from the private and the industry, could share data, and also to provide this the test and demonstration basis for the interested parties. So Center Denmark is we have, like in the board of directors, we have a number of DSOs. The TSO in Denmark has some 4 major universities in Denmark, some district heating companies, and basically it's a digital innovation hub, which is recognized by EU. We are also a digital platform provider. We have some living lab and test beds. And also we are independent and non-profit organization. So basically, also it means that, doesn't mean we don't do any commercial activities, but because we do have some activities in that line, but it's non-profit at the end. So when the center was established to sort of have this common area for sharing the data and knowledge, we got this project, Flexible Energy Denmark, which is led by DTU. It's a relatively maybe medium-large project, close to 5 million euros in the budget. So the idea there is to develop tools and solutions mainly based on the data to enable flexibility or to unlock flexibility in the sector. So the way the project is organized is that we have some living labs or some demonstrators, both from the DSO, from district heating companies, and from public sector or some of the municipalities, where we get the data into some data lakes that I'll talk about in details later on. We'll develop some tools and models, algorithms that comes from, again, third parties, researchers, and we build some solutions. So this is a sort of a project, a work package that I lead, where we combine all the knowledge, and it's an iterative process. So if something needs to be changed, we go over. And here what we have is some products. So this is some third-party products or software tools that are already there by our industry partners that they need to improve. So that we collaborate and try to improve them based on our needs. And all that is just to enable us to unlock some flexibility. But the main focus is on the data. So going back to Center Denmark now, once we have all these, we decided to say, okay, if we have, I mean, what is the whole point? Well, something that we extensively see, at least in the research project, let's say in Denmark, I don't want to generalize that, but being able to, so bringing connectivity into research, because usually what happens in research project is you have some great things done, but if there are great modular stuff, they lead to a great publication, but most of the time they are just left on somewhere, some repositories, and not used. So what Center Denmark tries to do is to collect all these models, all this information, and sort of host it under services, so that could be used for follow-up project, for follow-up research, and so we can have these no knowledge is lost. But most importantly, what we have witnessed is that in this area we lack a bit of, well, a bit more than a bit of skills or competencies. So because the domain is so much interdependent, so much relying, it's no longer just a power systems problem or software system. You need a combination of skills to be able to handle this. And we can see this already in research, that you have both from applied mathematics to power system people or software developers that are working in the same domain. So the domain is quite diverse, and this is what Center Denmark tries to achieve. Of course, the services are expected to be 24/7. So the idea is that once you have these data in the data lake, people should be able to access it at any time. And yeah. So when it comes to the data and the data lakes, how these data are transformed or where they are going to be. I mean, the data would come from the bidirectional communication from the living labs. The data lake would act as a broker infrastructure among many partners. And it should also be easy to host tools and solutions from other parties as well, including the research models. So what we have at the minute as part of the project and the Center Denmark is this sort of an overview of the back end. So how things are done in sort of implementation phase. So at some point we have time series data. So these are not real-time data, just batch of data that you will use some SFTP server just to send data to the data lake. In some of the cases, we are actually more advanced, where the building management systems are or have the APIs, REST, MQTT, or different sorts of APIs that we can fetch the data. And another ones where we are using more IoT and forecast data, because I mean, as it was mentioned earlier, at least forecast data are quite important in this sector. So we get the forecast model and forecast data from third parties. And then the data is stored in the backend using different storage systems. But then the same data could be used for training and computation using different programming languages. The data lake in itself is quite complex because, as I said, we are getting all sorts of data from real time to sort of historical data. And also when it comes back to the users have different needs. So again, when it comes to real-time data, or even sometimes sending the signal or set point back, it needs to handle it, which we are doing right now. So again, in one of the use cases where we have some summer houses, we use power to heat, or where the summer houses are equipped with swimming pools. We get the readings from the sensors from here, and then we'll send to the right models to our university partners, and then generate set points and send it back all through the systems. And of course, all of it is orchestrated, and we use different systems in here, including Docker and Grafana for visualization and Kubernetes for resource management. Some of the use cases that we have, actually, it's so Trefor is a DSO where we are monitoring some of their feeders, and we have also access to real-time smart meter data. We have some district heating companies, and all in all, we are looking into sector coupling, but the main focus is on the data. And when I said at the beginning that we are sort of in transition level, we mainly focus on how these data can bring all these values. So what we have witnessed, at least on the ground compared to the research level, is that actually digital readiness levels vary among partners. I mean, we have partners very advanced; they have almost everything in terms of the setup API is ready, and some still sending data like CSVs and very old-fashioned, or at least in the domain that it shows the gap, and that's also creates a problem. And also when it comes to data sharing, another critical aspect is data privacy, because at some point we are dealing with their customers' data. Also, it's business sensitive data, because some of these people are working on the same domain, but they're also business competitors. So how much do you expose yourself? But again, when it comes to digital platform providers, we think or believe that they are kind of an enabler for us to ease this digital journey, because you need some centers or some places where you trust that you can share your data, both from the individual perspective and from the commercial side, and these that are the center point. And I know that there are similar probably initiatives in the UK, but what we have, at least in Denmark, we see it more because the focus is a bit more sector coupling. We think it's a bit more comprehensive.
Pascal, that's time. If you could just wrap up, that's
yeah.
helpful.
I think that's me. That's the conclusion. So I think what we need to have is, at least when it comes to data, to have secure and reliable information, from data sources. And we need to be able to try and test that in living lab environment or in real demonstration. I think that's it. I'll just finish here, and thank you. Sorry I had to rush through some of the slides, but if you have any questions, please get in touch.
Thank you very much. So our next speaker is from University of Exeter, and it's Emily Judson, to talk about data governance challenges emerging from energy systems digitalisation in the UK. So over to you, Emily.
Thanks, Sarah, and sorry for the horribly long title as well. Let me just share my screen. All right, could you just confirm you can see my title slide, please?
Yes, I can.
Fantastic, thanks. Yeah, so what I'll be presenting today is essentially walking through some of the findings from my PhD research. So I'm currently writing up my PhD, and I'll be looking specifically at data governance challenges. So I won't spend too long on this because I know others have talked a lot about the context. But yeah, my research is also framed within kind of the 4D setup, looking at digitalization as just one kind of trend within energy system change. And also, as Razgar mentioned, the kind of increasingly porous sector borders between the energy sector and others, particularly in the data domain. So I won't spend long on here, but that's just a bit of context. And then just to explain a bit about kind of what my research is doing and where the data is drawn from. So as I said, I'm looking at governance challenges emerging from digitalization of the UK energy system. My research was conducted over the last couple of years, and it's a mixture of primary data focused on UK and also a literature review, which is a bit broader. So hopefully some of this will have some kind of international applicability as well. I've taken a qualitative approach focused on interviews and workshops, and I've used a targeted sampling framework to try and ensure that the diversity of views that I source my data from are representative of key stakeholders across the UK. I should also say as well, not on this slide, that my research was kind of in two parts. So first of all, I asked my participants about emerging governance challenges. I then asked them a series of kind of questions designed to build discourse and future imaginaries of what our future institutional architecture could look like to meet some of these governance challenges. So what I'm presenting draws on kind of both sets of questions. So yeah, these findings focus on what I've looked at in terms of data governance, but also just to flag that this is just one of 5 main thematic areas coming out of my research. Others include things like governance of algorithms and automation, consumer protection, skills, regulation, etc. So if you've got any broader interests and would like to chat, my email's at the end of the presentation. But yeah, moving on here, this is a diagram of essentially what my main findings were in terms of data governance challenges in the UK. So net zero 2050 is obviously the big target that's contextualizing this in terms of policy, which is obviously legally binding as well. And the 6 kind of medium blue items that you can see in the circle outline 6 kind of main considerations for data governance that will need to be thought about as we build in future. So to go through each of these briefly, by language, I mean kind of definitions and terminology, making sure that these are interoperable within the energy sector and also within adjacent domains. Data quality emerged as a big challenge. I'll talk a little bit later about bias as well. I know that's something that some people term a quality issue and some people term elsewhere. Discoverability is something that came up a lot, both in terms of data sets that energy sector stakeholders simply don't know exist, and data sets whose contents are quite undiscoverable. So you might have just a title of a data set and you don't know what it is until you've paid for it and got it. Data sharing and barriers to sharing also came up a lot, of which there were 2 main aspects. First of all, access to data. So this is talking mainly about data that has some form of restrictions and isn't open. And also licensing of data, which is quite holistic. So, you know, it's very basic stuff. Does all data have a license? Is it clear? Are we using similar terminology? You know, is it comprehensible, or do we need to use a lot more legal resource to interpret it? Privacy's come up in some other conversations, so I'll leave talking about that for now. And also, one thing I wanted to spend a bit of time on, because it's not a particularly kind of common data governance focus in the energy sector so far, is my participants had some quite in-depth discussions about new responsibilities that are emerging from sector digitalisation in the UK that are playing out in real time at the moment. And yes, this is kind of at the bleeding edge of change, so more in universities and startups than possibly among some of the more established stakeholders. But 2 of these main things relate to harms detection and emergent monopolies. So just to explain a little bit about what I mean by this, harms detection was flagged in relation to essentially new insights that can be generated from energy and related data that people don't necessarily mean to generate. So the example that was talked about quite a lot in my research workshops was domestic violence. So I had a couple of participants working with heat data in particular who reported that essentially their companies could see patterns in heat data that were quite indicative of certain forms of coercive control that are quite well established in the broader literature. They could also see people with health problems, they could see fuel poverty, they could see a whole range of very, very personal information, and they weren't sure whether this might generate some new responsibilities in terms of kind of, if you detect a harm, what are you supposed to do about it? Should relevant authorities be alerted? Or should companies in this space stay completely clear of these ethical issues? What's the appropriate way to handle this? And how does this interact with existing privacy legislation like GDPR, or in the post-Brexit context of the UK, the new data rights regime, which is currently under consultation? So that was one quite interesting area that had come out that I don't think is particularly well talked about in the policy landscape at present. My participants also talked quite a lot about emerging monopolies. So Razgar talked a bit about data and digital platforms, or data lakes. These were flagged as one potential source of emergent monopoly that might need to be brought under regulation. New forms of data sharing infrastructure might also form a new monopoly. But there was also some other discussion about things like the definition of monopoly or oligopoly that we use in energy sector regulation. So for example, if we talk about data monopolies, are we only talking about the ones that are emerging on top of existing physical sort of infrastructural monopolies, so like DNAs? Or are we talking more widely, potentially about new sources of kind of essentially concentration of economic power and knowledge that might be through data set combination or through a platform or new stuff? So that's a bit of a kind of brief talk through the main areas of consideration. My next couple of slides look at challenges and kind of suggested responses. So some of these were outlined in the previous slide, but the main challenge associated with kind of language differences or a lack of standardized terminology was the lack of semantic interoperability, both across the energy sector and with adjacent domains like transport or heat. Common quality issues flagged includes kind of noisy data, which, as Razgar also flagged, sometimes can be got rid of and sometimes is just a feature of working in this area. Inconsistencies in granularity, unclear measurement units, and irregular data uptake frequencies, basically all of which are factors that make data harder to work with, or a bit more, it's harder to build a business model around data where you don't know, for example, if it's going to be updated weekly or monthly. Bias also came up here, but as I've said before, this is flagged variously as a quality issue or as a social issue. So for example, data sets that have a known kind of skew towards sampling particular stakeholders or a particular geography may be considered biased, but this is kind of framed as a quality issue, where there's other participants discuss bias as a social issue, for example, where you have data sets that only represent kind of early adopters of technology, which are from higher income households, which reflects kind of a broader social structure of who can and can't afford smart technologies in the digital transition, not simply just a data problem of the sampling was skewed and it could be corrected. So that was raised as a challenge. Discoverability is something that I've talked about before. So there's a huge range of emerging data sets in the UK, but sometimes they just can't be found. So you might have a data set kind of hidden within a company's information management structure that could be shared and could be really useful, but external stakeholders don't know where it is, they don't know what it's called, and they don't know how to access it, even if technically it can be shared. And also there's a lot of data sets which don't have particularly descriptive metadata, so you just don't know what they contain. Moving on from that, the three main challenges associated with data sharing were flagged to be non-standardized access mechanisms. So essentially, if you go to two different data controllers, you might be asked to give different proofs of why you can or cannot access the data, or to pay quite different amounts of money for very similar data sets. And this was flagged particularly across different geographies. You could be asked for very different proofs or requirements for simply different places rather than different sensitivities of data. Ambiguous or missing licenses are a huge problem, which is particularly applicable to open data. So lots of data that is published on the internet and might be accessible can't technically be classified as open data unless it's appropriately licensed, and this massively reduces the actual usability of this, or can lead to legal problems for companies or researchers that do use it and later find out that it was incorrectly licensed, or the license may have been hidden in a general publication statement somewhere else on the website that wasn't clearly attached to the data set. And the final thing that came up was there's a scheme, or actually it's coming into regulation, I shouldn't say scheme, a new part of principle-based governance in the UK called Presumed Open, which is coming into the licenses for DNOs in the next price control period, where essentially data has to be assessed in something called a triage, and companies are encouraged to make data open wherever possible. So this is the principle of presumed open. This broadly was considered a very, very positive thing that will hopefully improve data liquidity and transparency across the system. However, currently there is a perception that the decision on whether data sets can be open or restricted lies more within the data controller's remits than elsewhere, and there might need to be some kind of independent dispute resolution. So that's kind of challenges related to sharing. Privacy related challenges that were discussed mostly focused around excuse me, poor public trust in privacy practices, not actually for established energy entities, but mostly kind of newcomers to this space that might be moving across from the broader digital sector, where there have been quite known and quite well publicised kind of privacy focused issues. And I won't talk much about new responsibilities, as I spoke about them a little bit on the previous slide, but yeah, they were focused as challenges as well. So the next thing that we talked about was potential responses to these, and I've put this up as kind of a summary slide, but I won't go through it in detail, as I'll circulate the slides afterwards, and it gets quite technical. But the thing that I wanted to draw attention to really is that participant responses to, or suggested responses to, how these governance challenges can be improved focus really on a couple of main areas that are highlighted in bold in the orange rectangle. The first one is around standardization. You'll also see that transparency or transparency related activities come up a lot. And so I just wanted to spend a couple of minutes talking about these main kind of response types. So as I said, standardization was the most common kind of ask from participants to improve data governance in a variety of areas, included, for example, a metadata standard, standardized quality metrics. And standards are quite interesting because there's in the broader literature, so not just looking at energy, but also looking at other sectors that have rapidly digitalized like medicine or bioresearch, finance, etc. Standards are kind of being tracked as a type of governance institution that is becoming more common and has more kind of pervasive power to regulate, you know, in the broader sense of the word, digital transitions. So something that's particularly interesting about standards is also that they are highly networked institutions, so that the way that they're built in the UK, and I know a lot of other countries, is they're built through attempts to form kind of industry consensus. So you have large consultation mechanisms, and then you have kind of ongoing governance processes where people can feed in if the standards aren't working. And this in some ways can be great because it means that you have more voices in the room forming the standard, but if these processes are carried out without adequate transparency and kind of accessibility mechanisms, the kind of network nature of standards means that they can become a vehicle for vested interests, which can then shape kind of how things are built and conducted for a long time into future. So they're quite an interesting new focus of governance that I personally think will probably become more and more important as digitalization progresses in the energy sector and kind of interacts with standards and digital governance in other adjacent sectors as well. So that's something on standards. A quick note on transparency was that it was the most commonly referenced principle used to characterize improvements to energy data governance. It has been talked about quite extensively before as well in terms of policy work around presumed open. But my particular research data framed it as most important in areas where there are identifiable public impacts or expected public scrutiny. And the reason this came up specifically is that digitalization is very closely associated with energy sector decentralization and increased activity levels of the general public, new organizations, and kind of stuff happening at much smaller scales. And if you have decentralization to that level, there was a general feeling among participants that you should also extend opportunities for scrutiny, and kind of that requires transparency to happen to new actors to make sure that there's governance kind of happening at all levels of decentralization, not forming old patterns of being quite centralized. So as was in the previous slide, this also forms the principle behind suggested activities such as bias audits, data cataloging, or improving metadata. And the one kind of main area of tension that came out around this was that transparency is great in kind of principle, but how do you actually enforce it when there might be vested kind of interests at play here?
We're just about out of time now.
Yeah, this is
thank you.
Final slide. So yeah, the one area that I didn't include on my sort of summary slide was new responsibilities. They formed quite a lot of discussion in terms of challenge, but essentially what I found is that no one really knows how to address these, as these are quite different sets of responsibilities to what the energy sector traditionally has to tackle. And this is an area that was essentially suggested for further research. So I won't say too much more about that, but if you're interested, then happy to answer any questions. Thanks.
Great, thanks very much, Emily. So our last speaker before the break is Jake Verma from Energy Systems Catapult, presenting on delivering a modern digitalized energy system. Jake, over to you, thanks.
Thank you very much. I'm just going to share my screen. And thank you for having me today, and to the speakers that have come before. Just as a heads up, there will be some overlap with what Emily's just said. That's only because her research has been excellent, and we've really used quite a bit of it to influence our work as well. So with apologies to the audience for any repetition therein. So I'm just going to start the timer for myself. Okay, so my name is Jake Verma. I'm a senior consultant in the digital and data team at Energy Systems Catapult. For those of you that are unfamiliar with us, we're a not-for-profit organisation that are specifically in our team working to help the energy sector with their digitalisation journey. And the way that we've prioritised that over the last couple of years is by focusing on two aspects of it, which is releasing more data for research, business and SMEs, community interest groups, etc. And the others is by the other method is to try to promote digitalization. So that's moving away from Excel sheets and documents and more towards using software tools, modern practices and data science to transform the way in which organizations like network operators and other energy sector participants function and how they work. So we've got two major sort of strategic streams. So the first at the bottom you'll see here is what we published in 2019, which is the Energy Data Task Force. So this focused on data visibility and infrastructure and asset visibility within the sector. And then today we're working on a digitalization task force, which is an altogether much more complicated set of recommendations. And the objective of this is to embed a set of really key objectives to government and to Ofgem in order to make sure that we achieve a modern digitalized energy system that's fit for getting us towards zero carbon and fighting climate change. So I'm not going to go too much into the recommendations of the Energy Data Task Force, but I'm going to sort of focus on these three pillars, the progress so far. So the three major things that came out of the Energy Data Task Force was that we needed to focus on data visibility, infrastructure and asset visibility, and digitalization. So on the first pillar on data visibility, as Emily already described, we've really been focusing on this principle of presumed open. There has been great support and for that through data best practice, and that's going into the RIIO-2 license condition. So all of the network operators will be obliged to triage their data to justify why it can't be shared. As Emily also said, there needs to be support for some of the legal challenges and the commercial triage is needed. So there's still quite a bit of work to do on that. And I'll touch on the work that we've been doing with the specific network operator later on in the presentation. The visibility of data. So again, as already previously mentioned, the best approach to make data discoverable is to catalog it, and there has been slow progress, but there's been a flurry of activity over the last year, and the timelines look good on creating that cross energy data catalog, not necessarily a data portal or a data lake, but just to raise the visibility of the information that exists out there in the sector. On infrastructure and asset visibility, this is about registering the types of energy infrastructure that are out in the network. So, for example, if you want to connect a new solar or wind farm, you need to know where the assets are, how much capacity they've got, what the constraints are, etc. Potentially, there's a real need to accelerate progress in this area and to leapfrog what we said as part of EDTF, essentially because we made this recommendation a couple of years ago as a compromise, and actually we've moved past the point of this being relevant now. So getting full asset registration now is of real importance. And then the digital system map. So we made this recommendation based off some of our colleagues in Australia and some of the success that they've had with the ARAMI portal, which is really, really good. There has been a pilot of this over the last couple of that was released last week or the week before. It has some kinks in it, and there's still a need for greater visibility and speed of work. So going forward with digitalization, industry support from energy is still strong and continues to be strong, but there needs to be more leadership from the top level, because essentially what we're hearing a lot from energy and the energy sector is that they're not quite sure how to achieve this. They like the recommendations and they think they're good, but they're not really sure how to get there. So we're working on some of those things as part of the digitalization task force now. So spotlight on data visibility. Over the last couple of years, so Northern Power Grid, UK Power Networks and Western Power Distribution have all started publishing data more openly through portals. There's a couple of examples of these. Electrolink and Icebreaker One have both deployed tools which have assisted in the understanding and the visibility of data. And Ofgem, Elexon, and BEIS have all published code or license changes that will enable the easier sharing of data. And on the next slide, I'm going to show you these are the initiatives that have taken place in the last 2.5 years since we published the EDTF. Not all of them we can take credit for by any stretch of the imagination, but what it does show is that there's a lot of significant activity going on in the sector within Britain to try and push this agenda forward. And there's been a lot of activity from a lot of different organisations that are trying to push this agenda forward. So we're really pleased about that. So significantly, there's been the Modernising Energy Data Access and Modernising Energy Data Applications programs. So what's come out of this is Open Energy from Icebreaker 1. So this will facilitate and enable the sharing of information and data, even when it can't be published as open. So what they're working towards is facilitating some of the shared data that has more complex commercial or licensing agreements, but still making it available for people who can use it, like academia or business or government. And then we're also supporting at the moment 5 projects through the MedApps program. These participants are looking to build applications that will solve some sort of decarbonisation challenge within energy. And as I mentioned, and I'll talk about in a moment, we're also working on the Energy Digitalisation Task Force, which I will come on to in a sec. But one of the examples was our Presumed Open Data Challenge. So this was a challenge we ran with Western Power Distribution. So what we did was we took the data and we took the data from a specific set of assets within a solar farm in Devon that was connected to the distribution network. And the challenge essentially was to design the control of the storage device to support the distribution network to maximize the daily evening peak reduction. This was done for each day of a week, and this was done over 4 weeks. We released 4 sets of data, and this was a sort of a constrained optimization and control problem under uncertainty. And we essentially marked a set of participants from a range of different organizations that were aiming to sort of essentially, how much can you reduce the peak was the very basic way in which we did it. So for each day, for example, what we would do is we would submit the information from the substations and also the information from the solar farm where it was available. And essentially, what the participants needed to do was essentially forecast to a pretty accurate degree over a half-hour period what the gain was going to be over time, and to then decide when they were going to charge the battery. So for the scoring metric, we marked them on their peak reduction and the proportion of solar energy stored in the battery and from the grid on each day. And the final score for the current week was just the average over each day of the week. And we actually got some really good scores from people who were extremely advanced in forecasting. We also got some really bad scores from people who were using off-the-shelf and sort of commodity machine learning algorithms that they just took from Amazon and didn't really tailor. So that was quite interesting to look at the way in which people are approaching this. And actually, the people who won were the real experts in forecasting, particularly solar forecasting. We had participants from California, from Texas, from various different places, and generally it was very well received. So the Digitalisation Task Force is aiming to take a lot of this a lot further, and this is a couple of these slides are still work in progress. So on the left here is kind of what we feel like we're moving towards, which is disjointed, uncoordinated, inefficient and expensive monopolies. And actually what we would like to do is create a consumer-centred or a human-centred, as I like to say, energy system that drives net zero and has consumer protection built into it as a constituent part. So our strategic aim is still the modern decarbonised digital energy system, and this sits at the centre of our recommendations. Then we move to the key outcomes. So we want to maintain the stability and the resilience of the current energy system, accelerate decarbonisation, have whole system optimization, which is based on, again, as Emily said, the vision of a much more decentralised energy system, and exciting tailored consumers propositions. As we all know, in the UK with energy, it's extremely fixed, and supply is demonstrates poor customer service. There's really poor products available for people. It's really bad. So actually moving the needle on that is really important in the way that people access services that are tailored to their individual situation. And the key recommendation themes, I'm not going to show any of the recommendations because at the moment the slide looks like a virus and we're going to change that. There's blobs around the outside. But what we're looking for is to embed digitalization culture within the energy industry, adopt digital security measures, and we've been working with Ola, who's here today, on some of those recommendations. Calibrating carbon and communication interdependencies. So this is about measuring the impact of carbon or the actual carbon that's being emitted on a sort of half-hourly or hourly basis rather than just on a yearly basis, which is the current sort of obligations of the ESG reporting standards. Open and interoperable standards, so Emily touched on this a little bit. New continuous digital governance, so this is around emergent monopolies and looking at the way in which where those monopolies may come from and how they function, and then unlocking the value of consumer actions and assets. This is really shifting the emphasis of the energy system away from just supply and just valuing supply, and also introducing the value of demand as well, and starting to put together ways in which those can intelligently match together to really enable real decarbonisation rather than just greenwashing of sort of energy products and services. These are really, they're going to change still. We're still working on them. Our timeline is to work to, we're going to be publishing in January. We're going to be heads down writing these recommendations down into tangible things that BEIS and Ofgem and Innovate UK can support over the next 2 months. And we're going to be doing a launch in the early part of next year. And what we're going to be doing is essentially this, similar to what we did before with the Energy Data Task Force, which is, although this is a sort of policy document, really it relies on the engagement of the sector to really drive the recommendations forward and really move the needle in terms of digitalisation to enable decarbonisation, essentially. So this is a call to action, I suppose, for the people on this call as well. We talked a lot about the availability of data. Really, what we're really looking for is, firstly, on the left-hand side, the Energy Networks Association has an energy data request tool. I would encourage everybody who works with energy data to use that if they can't find the information that they're after. Every request that doesn't get answered by DNO is another, essentially, feather in our cap and another round in the chamber, as it were, to really push the ENA to start facilitating access to some of the information, especially where there's high demand for it. Supporting the Smart Meter PAG, the Public Interest Advisory Group recommendations. So this focused on extending the remit of the Smart Energy Research Lab to provide anonymised energy demand data to more people within the sector. And also, as we said, quite a few of the network operators are publishing data. I would encourage people to go and start using that and really give them feedback when they don't have metadata that's suitable, or you can't find something, or the data is of poor quality. All of these things are really important, and the network operators and providers really need to know these things. And the feedback really helps them, because essentially they are right at the beginning of a journey. They don't really know what they're doing, and they rely on the feedback and the sort of intelligent participation of people such as yourselves to really move the needle, and so that they can provide a better service, better data, and they can improve over time. So that was a bit of a whistle-stop tour. Thank you very much for having me. You can email us at digitalisation@es.catapult.org.uk, or I'll put my email address in the chat box.
Thanks very much, Jake. So that brings us to our short comfort break. We'll still keep it at 15 minutes. We're not running massively late. So let's come back at 9. 9:35 UK time, and take 15 minutes now. Feel free to stay connected to the Zoom call and just turn your video and microphone off, so it's easier to just come back into the room when you're ready. And feel free to use the chat function to ask any questions of our speakers so far. We have one more presentation when we return, and then we'll go into our breakout rooms. So we'll see you at 9:35. Thanks. Colleagues, I hope you've had a suitable break there. So welcome back to this second part to the workshop. I'd like to invite Dr. Youssef Aglaghi to present on predicting the impact of climate change on performance of energy systems using machine learning algorithms as our next speaker. Youssef.
Thank you, Sarah. Can you please confirm if you can see my screen or not?
Yes, I can.
Okay, perfect. Well, hello everybody again. Sorry for the long title. This is actually a research-based presentation, so hopefully you'll find it useful. My name is Youssef Aglaghi. I'm a research associate at Newcastle University. Well, my background is mechanical engineering, but in the last few years, I have focused on data science and especially machine learning algorithms to predict the performance of energy systems, especially in the future climates, and also in order to optimize the performance of the energy systems, considering the impact of climate change. Well, basically in this presentation, I'm going to briefly explain how we can tackle climate change using machine learning. And also I'm going to share with you the works I have done in 2 different projects by using machine learning algorithms to optimize the energy systems here in the UK. Basically, we all know that the main factor contributing to the climate change is the energy usage. Basically, energy usage, majority of the energy sources that we use are coming from the fossil fuels. To be precise, 80% of the energy sources that we use come from the fossil fuels. Well, basically, demand for energy is increasing globally, and it is predicted that it will keep increasing over the next few decades, at least by 2040. Well, to tackle the climate change, we need a sustainable energy transition in order to decrease the energy demand and increase the energy efficiency, and more importantly, to switch to cleaner energy sources. Well, in order to achieve this goal, we need the collaborations of individuals, governments, and companies, like what's going to happen in COP26 in Glasgow this week. Well, basically, when we talk about the climate change, we normally reference the average increase in global temperature. In the last 100 years alone, the average increase in global temperature is reported to be around 1 degree Celsius, and the rate has been doubled in the past few years, in the last 50 years to be exact. Well, basically, when the temperature increases, the demand for energy increases, and it affects our behavior in producing the electricity, in consuming the energy. So it's very important to control the increase in temperature and achieve and limit it to the targeted 1.5 degree of Celsius. Well, here I have illustrated the temperature behavior for the Newcastle University, where we are located for 2 typical years, for 1970 and for 2080. Basically, in general, we can see that temperature in 2080 is higher than 1970. So basically, we can say that climate change is happening around us. But how we can tackle climate change using machine learning? Well, basically, we all know that machine learning has become popular in energy sector over the past few years, basically thanks to the high availability of data that are being produced and recorded by the multiple sensors and meters that are being used in energy sector. Well, in general, machine learning contribute to energy sector in grid management, in demand response, in predictive maintenance, in energy source exploration, and in energy consumption. Basically, here at Newcastle University, we thought that by integrating the machine learning algorithms and future weather files, we can gain some insight about the performance of the energy systems in future climates, so that we can provide some solutions in order to optimize the performance of energy systems in the upcoming decades. Well, basically, here in this presentation, I'm going to explain how I have used machine learning in 2 different projects here in the UK. Well, in the first project, my case study is a building, And in the second case, project, my case study was a cooling system, which was originally designed for the data centers. Well, the first project is an ongoing project at Newcastle University, where basically we try to integrate the geothermal system to the whole energy system, and basically we try to decarbonize the cooling and heating in a building using geothermal source. Well, the case study is the Urban Sciences Building, which is located at Newcastle University, where our team are based. Basically, Urban Sciences Building, or USB building, is one of the modern building in Helix area at Newcastle, at city center of the Newcastle. Well, basically, at this stage, we have started by modeling the building in Design Builder software, basically in order to investigate the performance of the system under different operating conditions, and in particular under different weather conditions. And also, we wanted to use this model as one of our sources in creating and in constructing a data set, a big data set that is required for training the machine learning model. And basically here, we have listed all of the possible parameters that can affect the building energy consumption in machine learning models. Basically, we are going to use all of these parameters as our inputs in our machine learning model. Here, you can see the first few rows of the big data set that we have constructed for the building. Basically, it comprises the performance parameters, design parameters, and climatic features here. Basically, all of the climatic features are inspired from the future weather files. Well, as I mentioned, one of the sources for our data set is the Design Builder model, and the second source for our data is the Newcastle Urban Observatory, which is the largest depository of publicly held data in the UK. Well, having developed the data set here, we have used a long short-term memory RNN or LSTM RNN algorithm, which is a type of artificial neural network. And it is basically, RNN is distinguished by their internal memory, and LSTM is an improved architecture of the RNN with longer and improved memory. Well, as I said, this is an ongoing project, but here I have tried to put the initial results that we have derived from the model. Basically, in the first figure, you can see the required heating load for the building for the year of 2030 and 2080. Basically, at the first look, we can see that the required heating load at 2080 is less than 2030, and it was somehow expected because basically the temperature by 2080 is expected to increase, so the required heating load will decrease. And quite reverse behavior happens for the cooling load here. Basically here we can see that the required cooling load for the building in 2080 will be higher than 2030. So basically it is because of the temperature increase that we expect. So one of the solutions or understanding that we can get from these figures is that we need to put more focus on the HVAC systems and cooling systems in the future building, especially in the UK, where historically we had, cold summers in the UK. And the second project that I have been involved in the UK was about the cooling systems in data centers. Basically, the case study here is a cooling system. It is an evaporative cooling system, and it is called dew point cooling system. Basically, this project was granted by European Commission, and it is completed at University of Hull in the UK. Basically, in a similar way, in this project, we tried to simulate this system in a software which was called EES software, and also we carried out an experimental research here, and we constructed a big data set for our system here, again comprising the operating and performance and also design parameters for the system. Basically, we wanted to forecast the performance of the system in future weather, and also we wanted to see what would be the impact of optimization algorithms on performance of the system in this project. Well, we developed different machine learning model for the system using different machine learning algorithms, and also we use different optimization algorithms to optimize the performance of the system and to observe the impact of optimization on performance of the system in upcoming decades. Well, basically the results that I'm going to share with you in the next slides are based on the deep neural network model. Well, we compared the performance of the system in 4 different climates around the globe, and for 2 years, for 2020 and 2050. In general, we concluded that the required number of operating hours for the cooling system will increase from 2020 to 2050, basically, again, because of the rise in temperature. But it will definitely affect the power consumption by the system, and it will cause the power consumption to decrease from 2020 to 2050. But we thought that we can control the power consumption and even significantly decrease the power consumption by applying the optimization algorithms to the system. Well, basically in these figures, you can see the annual power consumption for the system in 4 climates in 2020 and 2050. Well, basically in general, we can see that the power consumption by the base system has been increased from 2020 to 2050. But as you can see here, in all of the optimized system, the power consumption have been decreased significantly. So here, basically, we concluded that, however, the power consumption will be increased because of the climate change, but we can control it. We can decrease it by applying the machine learning algorithms here. Well, basically, at the end, I want to recap by this, that by applying and by integrating the machine learning algorithms and future weather files, we can gain some insights about the future performance of the energy systems, and we can basically come up with some solutions about the future, about the design of the future system. So we will keep actually doing our research in this area, and hopefully we will come up with some great solutions to optimize the performance of the systems in future. Well,